So we're going to finish up by looking at section 4.3. And we're going to solve some equations, and maybe we'll get to some inequalities that have rational expressions in them. Mostly we're going to focus on algebraically. Anything that we do graphically today is going to be only on the calculator. Graphing is not a good way to try to solve an equation, especially when the answer is a decimal. You can't graph it by hand and see the answer. So calculator, we can.
Sorry, what's the title?
Rational or equations and inequalities with rational functions. So just to jump ahead and kind of show you the problem, like one we're going to do, that's an example of a rational equation. And I'll show you how you solve it. So we're going to start out by looking at a word problem that's going to end up creating a rational equation for us to solve. In that problem, we're going to use an equation that hopefully you remember, distance equals rate times time. If you don't, oh, there it is. And what's going to happen in this problem is Sue is going to be traveling somewhere, and she's going to use two modes of transportation to get where she's going. First, she's going to take a train to do the first part of her trip, and then she's going to, she's going to drive first to a train station, then she's going to get on a train from there. So she's going to drive, and she's going to take a train. The distance that she drives to the train station is 30 miles. And she's going to travel a total of 120. So it should be pretty easy to figure out how far the train takes her. That's not really a good question. What we know is that the train, on average, is 20 miles per hour faster than the car. So the train, on average, is 20 miles per hour faster than the car. And so that's the setup. Now we just have to see what do they want us to find. Okay, find an expression that represents the time to complete the trip. So we're going to find a formula that represents the time to complete the trip. And specifically, they want us to use the letter x. And x is going to represent the speed of the car. You could also do it from the perspective of the speed of the train, but they want us to use x, and that be the speed of the car. All right, so let's think for a second about the time. To find the total time it takes for her to do this trip, we're going to have to find two things. What's the first thing we have to find? Yeah?
90 miles on the train.
Okay, that might be part of what we use. But I'm thinking of something else, just not even any numbers in it, just kind of an idea. Like, how are you going to find the total time to do this trip? Yep?
You have to have the speed of the car first, right?
Yeah, it's a little simpler than that.
Distance that she goes in the car and train.
Why do you need to know the distance? Why would you want that? What would you put right here in words if you wanted to find the total time? And this would be part of what you're going to find. Yeah?
Distance divided by rate.
For what? So there's a couple things going on in this problem. So when you say distance divided by rate, can you be more specific?
Would you do the distance how far the car went divided by the rate of the car?
And what would that give you? In general.
30 divided by x.
So what is that?
That would give you
They give you the time of how much the car travels.
Right, that's the time in the car.
Oh,
So to find the total time, we need the time that she's in the car, and what else do we need?
the time she's in the train.
The time that she's in the train. So time in train. That's kind of the big concept. Now we're going to break that down and figure out how do we represent it. So let's start with time in the car. So here's your formula. What do you get if you solve it for t? Yep. Distance divided by rate. So let's find the time in the car first. So let's call this time of the car. To find the time in the car, I need the distance in the car, which is how much? 30. And what's the rate of the car?
Next day.
Yep, they tell us the rate of the car. Just x. They say x is the speed of the car.
Oh, that's right, because rate is speed.
Okay, so there's the time for the car. Now we need the time for the train. So to find time, we do distance divided by rate. What's the distance she travels on the train? 90. And what's the speed on the train? X plus 20. Now, to find the total time, what do we do with both of those? We add them together. All right, so total time, which we're calling t of x, so the time as a function of x, is time in the car plus the time on the train. Now, we're probably going to want to write that all together with a common denominator, because that's going to make it easier to figure out some things. When you have two denominators, how do you find a common one? You multiply them together. You could multiply them, but I'm just going to leave it like that for now. What would you multiply top and bottom by here? You'd multiply top and bottom by x plus 20. And what would you multiply top and bottom by in the other one? Just x. So that's going to give me 30x plus 600. But I'm going to have 30x plus 600 plus 90x. So what's 30x plus 90x? 120x. Okay. So I'm going to keep that like that for now. But this makes any vertical asymptotes very easy to find now, because I can see the zeros of the denominator. And there's, we could factor out a number out from up here. You could factor a 20 out.
Wait,
Actually,
why does the denominator stay the same if you're multiplying both sides? How do you get the same thing?
Because on the left I have x times x plus 20, and on the right I have x times x plus 20.
Wouldn't that be 2 times x plus x times?
When you're adding, you don't add denominators, you keep them the same
Okay.
when it's common.
Oh, that's right.
Like 2/3
Yeah.
plus 2/3 is just 4/3.
Yeah.
You keep the 3 the same. All right, so here's the equation we just found. Okay. I wrote it this way, but I do want to copy down the other way we had it. 120x plus 600. Over x times x plus 20. So let's start with, vertical asymptotes. Let's do that. Regardless if the number makes sense in this problem, I don't care right now. What would be my vertical asymptotes in this one? Yep. And negative 20. I know negative 20 does not make sense for the speed of the car, but it is a vertical asymptote. What other kind of asymptotes do we have? Well, let's do the EDM, and that'll lead us to the horizontal. Now, be careful here. What's the highest degree term in the top?
X. Well, X1.
Whole term.
120.
120x. What's the highest degree term in the bottom?
X squared.
Right, you have to FOIL that out to see that. X squared. So what's my EDM?
120 over X.
120 over x. So now, using that, as x gets bigger and bigger, what does this fraction get closer and closer to? It gets closer to 0, but will it ever reach it?
No.
No. So the horizontal, again, anytime you write an asymptote, it needs to have an equal sign. Otherwise, it's not an equation. What else? We've got asymptotes, we've got the EDM, the zeros. So the 0 is where it crosses the x-axis. How do you find the x-intercept? You plug in what for what?
0 for sorry. 0 for y.
Plug in 0 for y. Well, that's y. So you're basically going to take your fraction and set it equal to 0. Well, what's the only way that a fraction can come out to 0? The numerator is 0. So to find the zeros, all we have to do is set the numerator equal to 0. That's all. So negative 600 equals 120x. And I think, yeah, we can divide by 120. And what do we get for an x-intercept? Negative 5. So we got the asymptotes, the EDM, we got the zeros, and now we want to find a complete graph. Complete graph means the whole thing, even values that don't make sense in the word problem. Okay? If it said, find a graph specifically for your problem about the car, then you would not include negatives.
Okay, so what do we get for the 0?
Negative 5, I think. I'm going to type in the second one because that's easier for me to do. I don't know, I think it's easier to type in. And then I'm going to do the bottom out because then that'll be even easier. X squared plus 20x. Okay, so there's our graph. We know that we have a vertical asymptote at negative 20. So let's go to negative, maybe negative 50. Let's go, I don't know, x represents speed, so that could go pretty high in this case. Yeah, let's just go up to like 80. Y min and max, not really sure right now. Let's just leave it like that. Okay, that's a pretty classic kind of graph we've had before. We get the curve in the lower left. I'm not really seeing much of it. Curve in the upper right, and then that kind of S curve in the middle. Now, if we wanted to look at this in terms of our word problem, which part of this graph would we focus on?
The one in the first quadrant.
Nothing in the fourth quadrant.
That's not the first one. The other quadrant.
Yeah, the first one.
Yeah.
So, as far as the word problem, all you want to do is focus on what's in quadrant 1. And essentially, the pattern here is x is speed. So the faster that you end up going, the lower and lower that the time gets. But eventually it starts to level off, and going a little faster doesn't make that much of a difference at this point. Now, it makes more of a difference for low speed, but at higher speed, it just doesn't make that much of a difference to go that much faster in this problem. So now it says that Sue has 2 hours to complete her trip. Find the speed she has to travel by car. We're not going to do algebraically because we're going to do a lot algebraically in a minute. Let's just do it graphically. So, what do you think I'd have to do to use this graph to find the speed it takes for her to do the trip in 2 hours?
Trace for x equals 120.
We're not going to use trace. We want to be able to calculate something exact here. What's that? Well, we're calculating an x value. We're calculating a speed. So we can't plug in a y value and calculate an x value in the table. You can do it the other way around. Any other?
We set like gradient intersect with the horizontal line.
Okay, so where do you want to put a horizontal line?
Oh no.
Why? What did I press? Well, you know what?
I was going to say 120 for the amount of minutes that it would take, but...
Hopefully somebody else has that typed in. So we're just going to use this. So where would we put a horizontal line?
My guess is 120, but that's probably not, because that would be pretty high up on the graph. That's not what we're looking for.
Yeah, we're not looking for when it takes her 120 hours to complete the trip.
Oh, okay. I was thinking it was like 3 minutes, so I just said y equals 2.
Yeah, set a line at y equals 2. And if you had that typed in on your calculator, you would have something all of a sudden that looks just like that.
Yeah.
And what would you do now?
Now you found the intersect.
Yep. Now you'd find the intersect, and right there is the speed that she would have to travel. And we're solving for x. Remember, x is the speed of the car.
46.5.
46.5?
Yeah, it's 46.457.
So if that's the speed of the car, if they asked for the train, what would you write? 66.5. Yeah, because it's 20 miles per hour faster.
Oh, I see. Okay.
Right, so all we had to do in this problem was come up with the equation and then calculate an intersect. Is there any question on how to find an intersect on the calculator? I would have showed you, but I don't know, it somehow deleted my problem. Okay, so solving graphically, not that bad. All we have to do is use an intersect. Now, if we had solved it algebraically, we would have had a situation kind of like this. Let's say you had, actually, I'll show you in a second. To solve this problem algebraically, what we would have done is taken our problem and set it equal to 2. So we would have had 120x plus 600 divided by x squared plus 20x. And we would have set that equal to 2. To solve it, we want to get rid of that fraction. So what could you multiply both sides by to get rid of the fraction here?
X squared plus 20.
Right. And when you multiply both sides by x squared plus 20x, it's a distributive property on the right. I'm sorry, it's a distributive property on the left, and the right stays the same. What kind of equation do you basically have there?
Y equals mx plus b. No.
No.
No, because it has a square. I'm just going to stop.
So what kind of equation is that? It's a quadratic. So we would solve that like we would solve a quadratic, and we would end up getting the answer that we got, which was, did you say 46.46 or something? Okay, 46.5. So if I solve it, let me show you what ends up happening. 2x squared minus 80x plus 600 equals 0. Let's use the quadratic formula and see if we get 46.5 miles per hour. What I could do first, divide everything by 2, just make the numbers a little smaller. Not much smaller, but. And we got negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, what I want to do is figure out what that number is under the square root. 4 times 1 is 4. 4 times 3 is 1200. What's 1600 minus 1200? 400. Now, let's see. We shouldn't get an exact answer here. Let me just see, what did I do? 2x squared. Did I copy what's in red, right? I think so. That was my original denominator, right? Yeah? Yes, that's it. When you move that to the other side, it's a minus 600. There. So that's a minus 300. So that's a minus. And now, there we go. What's 1600 plus 1200? 2,800. That's it. Now, I don't have to worry about the minus because the minus is going to give me a negative answer. And we're looking for speed. So the only thing you have to worry about here is 40 plus the square root of 2,800 divided by 2. Is that the answer that we got?
Yes.
Okay. So we get the same thing algebraically. The issue that we had here is we multiplied both sides of the equation by a variable. What variable in this case? X squared plus 20x. Whenever you multiply both sides by a variable, you can get an extra answer that shouldn't be in, that isn't really an answer. So that's called an extraneous solution. If you multiply both sides of an equation by something with a variable and you go to solve it, that's okay to do that. You can do that. You have to do that. But what that means is you have to check your answers and make sure they work. Because by multiplying by a variable, you may be introducing an answer into the problem that shouldn't be there. And that's called extraneous. Doesn't mean you did something wrong. It's just that's what happens when you multiply by a variable. So we have to check our answer. Here's a very simple case. What's the answer to that equation? X equals 1. Does anybody think that there's another answer to that problem?
I'm not.
Okay. I'm going to multiply both sides by the letter x. Okay? Do it on both sides. So now I have x squared minus x equals 0. All I did was multiply both sides by x. If you factor the left-hand side now, you get that. What could you plug in here to make this 0? 1. So the original answer is still part of this answer. But by multiplying by both sides by a letter, I introduced a second answer. What's the second answer? The second answer is now 0. But was 0 an answer to the original? No. So by multiplying both sides by x, I created an extraneous solution. An answer that shouldn't be there. I still got the answer that should be there, but I got an extra. So we just have to check. So the idea that what we're going to do to solve problems that have fractions with variables in them, we're going to multiply by the LCD. It's basically like doing something like this. And let me just put a variable in there. If I wanted to solve this equation, it'd be a lot easier if I didn't have any fractions. So what could I multiply everything by in that problem so that all my denominators disappear?
Make both sides equal.
I want to multiply everything by the number 6. Just multiply everything by 6. Times 6, times 6, times 6. In this case, I'm not multiplying by a variable, so that's going to work perfect. I don't have to check for anything extraneous. But now, all my denominators are going to reduce to 1. And I have a much simpler equation to solve. 9 plus 12 equals 5x. And I don't have to deal with any of those fractions. We're going to do the same thing, but with variables. Now, there is a pattern here. Something special is happening with that denominator on the right-hand side. Does anybody see what's special about this denominator? How about in relation to the other two?
Oh, so those are factors.
Those are the factors of it. This is x minus 1, x minus 3. I did the same thing up top. I made this number the product of those two. So when you found the least common denominator, this didn't have any effect on the problem. All you really had to do was find the LCD of 2 and 3. Same thing here. The three denominators are x minus 1, x minus 3, and then the product of x minus 1, x minus 3. So what's the least common denominator that I could multiply all these by?
X squared times 4x plus 3.
And can you tell me that in factored form?
X minus 1 and x minus 3.
X minus 1, x minus 3. So let's multiply this by x minus 1, x minus 3. This by x minus 1, x minus 3. And this by x minus 1, x minus 3. Now, something cancels out everywhere you do that. What's going to cancel out in this first term? The x minus 1s cancel out. How about the second term? The x minus 3. And the third term? The whole thing. So all you're left with on the right is 2. Now, did we multiply by something with a variable?
Yes.
Yes, then we may be creating an answer here that is not an answer. We need to check when we're done. On the left, you have 2x times x minus 3, which gives me what? 2x
X squared minus 6x.
minus 6x. On this one, well, nothing happens really. It's just positive 1 times x minus 1. This symbol goes with that number. But in this case, it's just a positive 1. So plus x minus 1 equals 2. And now, what kind of equation do I have? It's just a quadratic. These almost always end up being quadratics. So 2x squared minus 5x minus 3. And let's see if we can factor that.
Wait, would you?
So I know it would be 2x and x. How about my signs? Definitely going to be a plus and a minus.
How can you tell? I'm never good with knowing what signs to do.
There's a chart you can make, but the idea in this one is if the constant is negative, you have to multiply two things together to get a negative.
I see.
So it has to be one of each.
And how do you know which one's going to be positive?
I just took an educated guess.
Okay.
I just guessed. I could be wrong. And now two numbers that multiply to give me 3. Yep.
Yeah,
3 and 1. 2x times x is 2x squared. 2x times negative 3 is negative 6x. Plus 1x is negative 5x. Perfect. So now, what would be my two answers for x? 3. Yeah, that's the second one. And negative 0.5 or negative 1/2. Now we have to check those because one of those might be an answer that doesn't work. Let's go back up to our original problem. Remember these two numbers, negative 1/2 and 3. And what do you think about trying to plug those back in?
If we do, we should get 2.
Well, what would happen if you tried to plug them back in?
We'd be checking to see if it was the right one or not.
Okay, we'd be checking to see if it's the right one. And without going through it all, something bad would happen if you did something. Yeah?
I was just going to say they should be equal.
Yeah, well, they should come out equal on each side if they work. But I'm going to tell you, one of those works, one of those doesn't. Yeah?
There's a 0 in the drawing here.
What do you mean?
The second fraction.
Okay.
3 minus 3.
If you try to plug 3 back in as the answer, you're going to have 1 divided by 0 for the second fraction. So 3 is extraneous. And yes, I might ask you for that on the test. I will. So I'll give you 2 boxes, and I'll say one of these works, one of them doesn't. You'll have to find the numbers, and then the one that doesn't work, you'll put it in that box that says doesn't work. And the one that does work, you could check it, but negative 1/2 will work fine. Okay, but the 3 doesn't work. So there's 3 possibilities that can happen in a problem like this. You get 2 answers that both work. You get 2 answers, one of them works, one of them doesn't. Or you get 2 answers and they're both extraneous. That means there is no solution to the problem. Any one of those 3 things can happen.
Okay, so theoretically, should we test the negative 1/2 just to see, or like, do we know already that
You don't have to. I mean, I know it'll work, but you could check it if you wanted to, but
how do we know that there is a solution at this point?
because I told you.
Okay.
Yes. So yeah, the negative 1/2, it works. It's just kind of a pain to check it because it's decimals.
Yeah.
I mean, yeah, it's just you're going to have to square things that are fractions, so it's not an easy one to check. All right. Let's see. Down that. All right, let's try this. Let's start by factoring this side. How does the right-hand side factor? Or not right-hand side, I'll say the rightmost term on the left.
Oh, x and then x plus 2.
Okay. So this is really a step ahead of the last one because they already put everything on one side. You're going to have to get it equal to 0 anyway. They already did. You could do that first if you wanted to. So what could I multiply everything by? That would cancel all my denominators. X plus 2. So here, the x's are going to cancel, and I would just be left with an x plus 2. Here, the x plus 2 would cancel, and I'd be left with just x. Here, everything would cancel, and 0 times anything is still 0. Okay, so we have a 6. That's the easy one. 3x. This is the one that's a little more annoying because we have to FOIL it out. X times x gives me x squared. 2x minus 3x. And negative 3 times 2. Negative 6. That's actually kind of nice because what's going to happen there? Yeah, when your constant cancels out, you automatically are out of using quadratic formula. You don't have to because the constant is gone. Makes it a lot easier. All you have now is x squared plus 2x equals 0. And what could you factor out on the left-hand side? X. So that would give you 1 plus 2. No, x plus 2. And what would be your two answers?
0.
Negative 2 and 0. And what do we have to do? Go back up and check them. What happens if you plug in 0?
It doesn't work.
What are you going to do?
You can't plug in negative.
Can't plug in negatives?
You can't plug in negative 2 or 0.
Yeah, you can't plug in negative 2 or 0 because both of those would cause you to divide by 0 in a different spot. That means this is no solution.
Interesting.
So these are both extraneous. Any question on that?
So the negative 2 doesn't work in the second one.
Negative 2 doesn't work here, 0 doesn't work here, and neither one of them works in that version. Yep. I think this is the last.
Oh yeah, we haven't gone over inequalities.
So this last problem really takes us into looking at an inequality. Most inequalities we would solve on the calculator. This would be the same idea as where we graphed a line at 2 and then looked at it and found the intercept. Well, this time you would graph a line at 2.5. You would still find this intercept, but the answer wouldn't be x equals that number. If we want to complete the trip in under 2.5 hours, would it be anything greater than that speed or less than that speed? Right. Right. So if it says she has to complete the trip in 2.5 or less hours, find the speed to complete it in 2.5, and then say, okay, if she went at that speed or more, she would do it in under 2.5 hours. So that's an example with an inequality. Almost the same thing. We don't use algebra to solve it because the problem with the algebra is you're multiplying both sides by a variable. While with an inequality, what you multiply both sides by makes a big difference. Because if you multiply by what kind of number, you'd have to make sure you do something. A negative. And if I'm multiplying by something with a variable, then I don't know what I multiply both sides by. So I have no idea if I should be flipping my sign. That's why this approach doesn't work with inequalities.
Alright, so
Only works with equations. So let's try. Yeah, that'll be the last one. Let's just try it on the calculator. Okay, if you have a rational inequality, just plug it in on the calculator. So x to the 4th minus 3x cubed plus 2x squared plus 2 divided by x minus 2. So probably going to have a vertical asymptote at 2. Let's put another line at 15. And I'm going to just do the standard negative 10 to 10. And I'll do negative 10 for the y min, but what should I set my y max at least?
15.
At least 15. I'd probably even go up to like, I'll go a little extra. So we're looking for where that graph hits 15.
What happened?
Okay, does it look like it hits 15?
No.
Okay, so in that window it doesn't. And maybe it never does. But I should probably look up higher and see is there something up above the graph
See, like
that I'm missing.
it does intersect, just not it.
Right, maybe it does, maybe it doesn't. I don't know. That's why I'm going to graph a little bit more.
Okay. Guess not.
All right, so I still don't see anything. Let me look. I'm going to look a little further to the left and the right. Yeah, maybe it's no solution. Don't need to look any lower. That doesn't make sense. You don't have to go lower. Let's go up to 100. If we don't see it here, we're probably not going to see it. All right. So I don't see it. I don't see them intersecting. So the question is, when is that graph greater than or equal to 15? Never.
There is no solution.
That's a no solution. Okay, unless I typed it in wrong.
Matthias graphed it, he got an intersection.
Okay, I probably typed it in wrong then. Did I forget the divided by again? X to the 4th equals minus 3x cubed. That's still a good one to look at because that was an example of no solution. Now that I changed the plus to a minus, let's actually do the correct problem. Okay. So now
So it does intersect.
it does intersect, but I don't want to go all the way to. I want to zoom in more because I can't see what's going on when I'm zoomed that far out. And what I'm going to do is set my x min to like -5, x max to 5, and I think you'll see it a little bit better. Yeah, you can see it better now. So the question now is, when is it above 15? Well, two sections. Here and here. So we just have to find those two intersection points. So let's start with that one. That's at 2.22. What's the lower end of this interval? Like, this is asymptotic here, right? What is that asymptote? 2. So the answer is from 2 up to 2.22. That's this section. And then from, bless you, the other intersection point, second calc intersect, that's 2.68. And how high can I go in that interval? I just keep going to the right forever. So that is the answer. So we got a no solution the first time because I put it in wrong. Everywhere else, it's below that line. So don't worry about this part down here. Don't worry about that little part right there. Just focus on where it's above. Actually, it says above or equal. So technically, I can equal the 2.22. And I can equal the 2.68. But I can't equal the 2. The 2 is an asymptote. So the first time I did it, I did that. I meant to do that. All right. enough time to get the list of topics on the board
No.
right now, but I'll put it in the video. Okay, so I only got about 3 minutes, so. So just to simplify this, let's just make this 1 through 15 odd. So 1 through 15 odd, and then 20 to 22, 24, 28, 31, and 32. That might be 13, maybe 13 questions, I'm not sure.